everyone, this is Anya and Shubhoshri, and in this video we will give an overview of the demand and use of construction materials. We will also examine some differences between regional and industrial construction material and then discuss how we can make an informed decision about material selection for a minimum environment impact. By 2050, twice as many people will live in cities than in rural areas. It is estimated that half of the area that will be urbanized by 2050 hasn't yet been built. According to Google Flux co-founder Jen Carlile, the population which needs to be housed by 2050 is approximately 3 billion, which means considering we house 100 people per building, we will need 33 million buildings. With 250 people per building, 13.2 million buildings, and with 500 people per building, 6.6 million buildings. That's a lot of building, which means a vast amount of material will be consumed, energy and resource demand will rise. Thus, the what, where, and how we use material is crucial, especially when transitioning into a circular urban metabolism system, where material flows forms an important part of the cycle. Settlements in the pre-industrial era majorly used locally sourced material like wood from the forest, sun-dried clay bricks, hay for roof, stone from the hills nearby, etc., reducing the need to travel long distance and also easing maintenance. Consequently, the building styles were dependent on material availability and the technical know-how of using them most efficiently. Being region and climate specific, over the years, these material and building style became part of the cultural identity and collective memory. For example, in the Thuringian region of Germany, slate stone is used extensively due to its local availability in the Slate Mountains and easy processing thereafter. They are also very durable and require less maintenance, making them a characteristic feature of many Thuringian villages and towns. Similarly, in the rural region of Ethiopia, houses in most regions are round in shape with thatched roof. Walls vary from sticks to coarse planks or mud-plastered walls as per the availability. Materials used in traditional building styles were also heavily influenced by the climatic conditions. For instance, slate is adapted to the weather condition in Thuringia. It has relatively high thermal mass, which means that these materials do a good job of absorbing heat from the sun throughout the day and releasing it at night. On the other hand, the thatch roof in Ethiopia is a natural insulator, and the air pockets within a straw thatch roof insulate the building in both warm and cold weather. But this dependency on local materials has changed with industrialization and globalization, at least for the majority of the globe. Post-industrialization, factory-produced materials like cement, steel, glass, etc., together with technological advancement, revolutionized the way we build. Mass-produced materials are faster to procure, stronger, and more durable. Assembly line guaranteed greater precision and standardization. Availability of materials locally is no longer a deciding factor, with global transport costs decreasing exponentially. But these advantages came at an expense. The widespread global use of these conventional materials led to the development of an international style and the lack of region-specific architecture. Thus, cities across the world have begun to look similar. Furthermore, the mass-produced, globally transported materials are extremely energy-intensive, with high carbon emissions and embodied energy, making the building sector one of the largest carbon dioxide emitter. Thus, although the conventional materials have many advantages, often the ecological price to be paid is too high. Similarly, traditional materials, though seemingly have low impact on the environment, but they can be restrictive in terms of ease of use, maintenance, and durability. Hence, while selecting the material which fulfills our requirements and has the minimum impact on the environment, we have to consider various criteria like availability, durability, feasibility, maintenance, aesthetics, and probably the most crucial criteria, sustainability. In this video, we will cover the sustainability selection criteria. Apart from the many international certifications and declarations, which has been developed to assess the environmental influences of building materials like LEED, ISO, etc., when it comes to the sustainability of a construction product, it is important to look at the entire life cycle of the product. Life cycle assessment is one such procedure. It is a technique to assess environmental impact associated with all the stages of a product's life, from raw material extraction through material processing, manufacture, distribution, use, repair and maintenance, and disposal or recycling. According to their LCA performance, material selection can be subdivided into four main pillars, which are First, environmental performance. The major indicators are fossil fuel consumption, for example, in transportation, atmospheric pollutant potential, carbon emissions, embodied energy, and recyclability. The second pillar is economic performance, which includes, among others, the procurement cost and maintenance cost of the material. Third is building performance, which measures the properties of lighting, acoustic, thermal comfort, indoor air quality. And the fourth one is social performance, which refers to the effect on human health, cultural heritage, aesthetic aspects, etc. These systems and standards have been gradually implemented into software for efficient environmental application to assist building designers or developers to prioritize and assess the indicators. One crucial aspect of any LCA is the end-of-life stage, which can take two directions. Either the material is disposed, which makes the cycle cradle to grave, or it is recycled and reused, which makes it cradle to cradle. Ideally, the life cycle of a sustainable construction product does not end with dismantling, but forms a closed life cycle by returning the product to the manufacturing process after recycling. According to the principles of cradle-to-cradle building materials should be chosen such that it consists of renewable, easily recyclable, and long available raw materials. Now, to get a better understanding of how LCA can help us select, let us take a look at concrete and wood. Looking into the raw material extraction, concrete is made of components that exist in many places: sand, gravel, water, and additives in combination with cement, made of limestone and clay. The energy-extensive part of concrete's life cycle assessment is the manufacturing process of cement, for which limestone and clay are heated to 1450 degrees centigrade. Cement is therefore one of the energy-intensive raw material with high production-related emissions. In the phase of use and maintenance, concrete has very good properties and is often used in buildings following passive cooling concepts, where it is used for thermal storage due to its large usable mass. Finally, if a concrete structure is demolished, the material can be partially recycled, but only using cement as a binder, which again drops the sustainability score. Thus, although concrete as a construction material seems to perform well, it doesn't outweigh the energy-intensive manufacturing of the key component, cement, and the corresponding high embodied energy. In contrast, wood is a natural resource, making it readily available and economically feasible. It can be directly extracted from sustainably managed forest, and its processing requirements are also minimum as compared to concrete. In the operation and maintenance phase, wood is known for its thermal as well as acoustic properties. Finally, when it comes to demolition, wood is the perfect example of an environmentally sustainable product, since it is biodegradable and renewable and carries the lowest carbon footprint of any comparable building material. This can be further clarified taking the example of a 1,000 square feet house. With concrete as the primary material, the approximate net carbon dioxide embodied is 45 metric ton. To offset this amount of carbon dioxide, one has to plant 225 trees. But changing the selected material makes a stark difference. Using wood as the primary material, the amount of embodied carbon dioxide reduces to 24 metric ton. That's almost half when compared to concrete. This brings us to the end of our video. Summing up in 3 points. First, although the dependency on local material has changed with industrialization, and now we have access to material from all across the globe, one should consider that material selection is dependent on climate and in turn influences regional identity. Second, since the amount of construction activity required to meet future demands is very high, we have to select the construction material very judiciously. From the example comparing carbon dioxide emission from constructing a 1,000 square feet building with concrete versus wood, we can estimate the impact material selection has on our environment. Last but not least, the need of the hour is the sustainability of a material, and life cycle assessment is one of the definitive indicator. Thanks to the huge pool of information available at our tips and the technological advancement, we can now make informed choices about the materials to be used, increasing resource efficiency and embracing an urban transformation towards circular urban metabolism. The choice of material need not be either or, but rather can be a composite of traditional sensibilities with modern advancement, keeping in mind sustainable outcomes. Thank you all for your time. Hope you found the video informative and we look forward to your feedback. Signing out, Anya and Shubhoshri.